Hello everybody, Philip Whiteman, Laketec Communications. This is a follow-up to our YouTube video that we discuss VXLAN, where I'm going to go into the basics of VXLAN with a graphical demonstration, and then look at some deployment methods that we can use to simplify VXLAN deployment. So to start off with, we'll go ahead and just go over some of the basics here. So the big buzzword today is fabric. So what is a fabric? So a fabric is nothing more than a bunch of interconnected devices that can transport data. So if you have a network, you have a fabric. So this is a basic basic visual of a campus network where we have core, ag, and access. This is a fabric because we're transporting data across it. We have had centralized overlay fabrics for years. So here we could see that we got access points that are tunneling traffic to centralized controllers. This could be, PAPI, GRE, CAPWAP, IPsec. There's lots of different tunneling mechanisms. GRE, if I didn't say that already. We have switches. Ruba can actually tunnel traffic just like access points can to a centralized point. So this is what we call a virtualized central, excuse me, a centralized overlay fabric, a virtual centralized overlay fabric. So when we start talking about VXLAN, we're talking about the distributed overlay fabric or a virtual distributed overlay fabric, where now instead of sending everything to a cluster of controllers here, or gateways, we can now send traffic from one switch to another. We can send our layer 2 traffic this way. So this is using encapsulation, VXLAN encapsulation, just like the previous slide we're using GRE and PAPI for that. Now we can extend layer 2 from one switch to another switch across the routed infrastructure, which we'll get into. So that's a super high level definition of a distributed overlay fabric, and that's what VXLAN is. Here's another example where we were just looking at a diagram like this here, where we can have multiple fabrics where we can extend layer 2 from one fabric to another. Maybe these are different campuses across the state or across the country. So we could do intra and inter VXLAN overlays. Okay, so why would we want to use VXLAN? So in the data center, VXLAN's been in use for quite some time. It's actually been around in the LAN infrastructure for quite a while as well, or the campus. But the reason data centers have been using it for a while, you can imagine that in a data center, when we're leveraging vMotion technology, we are moving a virtual machine, let's say at an ESXi host, from one ESXi host, maybe one data center, to another ESXi host in another data center. And oftentimes those data centers are separated by layer 3 boundaries, or they should be, in order to get optimize traffic flows there. So when we do that, if we have a client, let's say in data center 1 on VLAN 100, let's say he's got a static IP address, let's say 10.10.100.10, and he gets vMotioned off to the other data center, he needs to maintain his IP address, which means his VLAN needs to be there at the other data center, which means that we need that VLAN extended to both those data centers in order for that vMotion to be successful. So having layer 2 extended between two data centers, especially across a WAN link, is not efficient. So we're going to use VXLAN to route across that environment instead of having layer 2 across that environment. So that's one of the major benefits of VXLAN. Another one is microsegmentation. So first, what is microsegmentation? Macro segmentation is basically putting devices or users onto different layer 3 networks. So I've got a user on VLAN 100, I've got a user on VLAN 200, two different networks, two different layer 3 networks, and when we place them on those separate layer 3 networks, that is called macro segmentation. So in a macro segmentation world, we can segment those users not only by the layer 3 boundary, but we can put in policy or ACLs. Maybe those layer 3 boundaries are up on a firewall, Palo Alto firewall. We're implementing policies. Maybe we have ACLs at the layer 3 boundary for the network at the gateway level, or maybe a little higher upstream, where we are now separating that traffic. So macro segmentation is putting devices on separate layer 3 networks or potentially separate VRFs or both. Microsegmentation is when we are segmenting users on the same layer 2 network. So user 10.10.100.10 with another user 10.10.100.11, we could segment that traffic so they can't hear one another, they can't talk to one another if we choose, through microsegmentation in the same network. And VXLAN is going to enable that for us. Another benefit is if you'll see here on the next slide that we are going to push layer 3 down from, say, the aggregation or collapsed core down to the access layer so that we can take advantage of VXLAN because that is a requirement. And when we do that, we are no longer creating layer 3, say, at the core ag, and then trunking and tagging it down to the access layer. In some instances, we're trunking and tagging that down to multiple aggregations and access layer switches. So we can eliminate the need to do that. That's probably not the biggest benefit, but it is a benefit. We can reduce or eliminate spanning tree. So again, we're going to get into this, but if we have layer 3 at the edge, we're not trunking and tagging layer 2 up to the aggregation layer and further. So because we don't have layer 2 between devices anymore, there's no need for spanning tree. And another benefit that's not on here, which actually should be on here, is we're reducing our broadcast domain. So instead of that broadcast domain extending anywhere where we have that layer 2 VLAN, it's only going to be local to the switch that the client is on. And we will talk about that. So there's 5 benefits of implementing VXLAN, why you might want to do it. Okay, so here we have a depiction of a standard campus network where we have core, aggregation, and access, where oftentimes our aggregation layer is separated from the core via point-to-point links. This is a pretty typical design, and then down between the aggregation layer and access layer, we're trunking. So might have lags here, but this is typically all layer 2, and then we have our VLANs defined here. So in this design here, if this client over in VLAN 100 needs to talk to this client on VLAN 200, it's going to route to get there. It's going to come through the, maybe hit its gateway here at the layer 3 level, which routing says take it across the core, back down to this other aggregation layer, back, and then switching through layer 2 through the switch to reach this client. So very typical. In some campuses, we may have the need to have layer 2 adjacency between clients because an application requires it. Our maybe multicast requires it, or different mechanisms require layer 2 adjacency between these two clients here. So in order to accommodate that outside of multicast, so let's say broadcast, in order for this guy over here to discover the MAC address of this guy over here because he needs to communicate with him, he needs to send out a broadcast for that. So for this to happen in this particular diagram, we would have to have VLAN 100 here and here and here and here and here. So we have placed that broadcast domain across all of those switches in the environment, so that is not an efficient design. We typically try to avoid that. We try to, maybe have VLANs 100, 200, 300 here in this campus, where in this campus we have VLANs 101, 201, and 301 to prevent having to have that broadcast domain everywhere. But some campuses just require that we have clients across campus that can reach each other in layer 2. So not efficient at all. So we're going to use VXLAN to help address situations like that. Okay, so when we implement VXLAN, it is a requirement that we move layer 3 to the edge. So I should say it's a requirement to use Anycast gateways. So we have just moved layer 3 from here and put it here. So now all of these links are point-to-point layer 3 links. And I will say, we can have hybrid environments, of course. We can still trunk and tag. We can say have VLAN 300 still doing our traditional trunking through here, but then say maybe VLANs 100 and 200 are configured for VXLAN, and that we will route across this environment. So we'll encapsulate their traffic and send that across this environment to reach the other side. And we accomplish that by putting the layer 3 down in the switch. And when we do that, of course, now we don't need spanning tree because there is no layer 2 on these links. So we don't have to worry about tuning spanning tree. We don't have to worry about we don't have to worry about the broadcast traffic utilizing links, going over these links. So again, if we have VLAN 100 here, And across the environment, every switch has got to process that broadcast, because the whole point is we're trying to discover, who owns a certain MAC address. So broadcast, unknown unicast, multicast traffic, all of that will be heard by all of the clients in when we do our discoveries like that. So now we have isolated that layer 2 traffic right here to the switch. So, and again, we'll use VXLAN to be able to stretch that VLAN 100 from one side to the next, and then we're going to utilize the switch itself so that the client can route off net to get off of the VXLAN infrastructure. And we do routing within VXLAN as well. But the point is that we're using Anycast gateways to take advantage of VXLAN. Okay, so some terms before we get to the next slide. So VXLAN, its full name is a Virtual Extensible Local Area Network, and this is our data plane encapsulation. So we are taking the layer 2 traffic and we're encapsulating it in the VXLAN header and then encapsulating that in an IP header, and then sending that across the infrastructure to get to the remote end. Again, the encapsulation. And I forgot to mention earlier, like a VPN is a form of encapsulation. So a VPN is a good analogy to say when I'm at home on a VPN into work, that I'm coming across any number of routers across the internet, and we don't care. Those routers don't care about my layer 2 traffic because it's all encapsulated inside of a VPN tunnel. So VXLAN is that for data plane in a campus environment or a data center environment. So a VTEP is the configuration that we place on switches to start participating in VXLAN. So in order to take a VLAN, I keep on using 100 and 200, but in order for VLAN 100 and VLAN 200 to participate in VXLAN, we create a VTEP configuration of the switch. And then within that, the VTEPs have a concept called a VNI, so a virtual network I think I should say identifier. I have a typo there. Virtual network identifier, which really is a VLAN. So when I have VLAN 100 participate in VXLAN, I give it a VNI of 100. I can give it any number I want, but to keep things sane, we should give it the same number that the VLAN is. And oftentimes you'll see it as like 10100. We'll append a couple digits to it, but you don't have to do that. So we define the VLANs that are participating in VXLAN by associating with the VNI. We associate the VNI with the VTEP, and then the VTEP then knows I am going to use VXLAN to discover and transport data for these networks. So that's a VNI. And then our other big long mouthful here are multi-protocol border gateway protocol, Ethernet VPN. So it's a mouthful. And really what that is a control plane. We can run VXLAN without this piece. So we could statically configure our VTEPs. So if I have a switch with a VTEP configuration, I can statically tell him about all the other VTEPs in the environment. I'd statically program them in. I'd statically program in all the VNIs. And what we're going to learn here in a little bit is that when we have a client come on the network that needs to learn about a client on the other side of the network, it still has to do a broadcast, right? So if client A on VLAN 100 needs to learn about client B on the other side of the campus on VLAN 100, still has to do a broadcast. So VXLAN will still do a flood and learn process. He will know all the VTEPs that are participating in the network that client's on, and he will then tunnel the broadcast traffic across the environment, across the routed environment, and then it'll egress in all the VTEPs that are participating on that VLAN so that the client on the remote side can hear it so he can respond back. When that happens, they then populate their tables, and all the VTEPs participating in the VNI now know where that MAC address exists, and they don't have to go through that broadcast any longer. So it's not efficient. The multi-protocol BGP EVPN builds tables of all the locally connected MAC addresses and then uses BGP to distribute those tables to all the VTEPs that are participating in the VLANs that it just heard that MAC address for. So now we can build tables and share those tables across all the switches instead of using the flood and learn process. So this allows us to do VXLAN at scale, and we call it the control plane. Okay, some more terminology. So we have what we call personas. So as we configure the devices to start participating in VXLAN, we have personas. Starting here with an edge persona. An edge is a VTEP. I don't know why they don't call it VTEP persona, but they don't. It's an edge persona, which basically means that it is going to be configured to with VNIs for the different VLANs that we have on the switch. And this VTEP is where we source our VXLAN traffic from and egress to another VTEP where that traffic may be egressing. So I don't know if I say it anywhere in here, but we have loopback interfaces, specific loopback interfaces that will source and terminate that that tunnel, and it's just the loopback IPs that need to be able to route across the underlay. So as long as all the loopbacks can reach one another, that means VTEP is able to establish tunnels with one another, and that's what a VTEP's doing. And we define the switch as an edge. Okay, we have a route reflector. So in BGP typically is forms in a full mesh. So every switch that is running BGP. So if we want to take advantage of that EVPN I talked about, where we build the tables and we share those tables with all the other VTEPs, we have to run BGP on these switches. So when we build that table, instead of this switch sharing it with this one, sharing it with this one, sharing it with all the other VTEPs that are participating in VXLAN, we share it with the route reflector. Then the route reflector will then share it with the rest of the switches on the device. So we don't have to have a full mesh topology. So that's what the route reflector is doing for us. The border router is how we're getting off VXLAN and forwarding across the underlay to devices not participating in VXLAN. So maybe we're going out to the internet. Maybe we're going to a DMZ. Maybe we're going to other places, in the environment that's not participating in VXLAN. We need a border router configuration to help us make that transition. We have a stub. So a stub is devices that do not participate in participate in VXLAN, but in a static configuration. Maybe they can't do the MPBGP EVPN. So we are statically configuring all the VTEPs on this guy and all the VNIs, so that at least we can participate. We can tunnel traffic from this guy over to this gateway. That's doing static VXLAN. So that's what we call a stub. So when we have static connected to non-static or a dynamic EVPN, we call that a stub. And by the way, these I have listed on here: Campus AOS 10 Gateway Cluster. AOS 10 is an Aruba term. And these soon will be able to do BGP EVPN, so they will not have to be a stub. Then down here is another example: Edge plus stub. So now we have maybe a switch that also cannot do EVPN. So therefore, we're statically configuring the VTEPs, but it can participate in that. In the fabric. Okay, so those are our terms. All right, so what does that VXLAN header look like? So, traditional Ethernet frame here. So maybe it's a client that, again, is sending out a broadcast, or, just establishing communications with his peer, on the same VLAN. This is a standard frame. So because the peer can't hear this traffic, or we can't switch this traffic because we have no layer 2 adjacency, we are then going to wrap the VXLAN header over that, where we have a couple unique values. Before I get to that, we're going to put a VXLAN header on it. Then our traditional UDP, so this is UDP traffic, it's not TCP, but UDP, and then wrapping IP around that. So from here, skipping this piece to here, it's a traditional Ethernet packet or Ethernet frame encapsulated inside of IP. Okay. But now we have the VXLAN header, so when this guy needs to talk and his peer is on another VTEP or another edge switch or another switch that's participating in VXLAN, it's going to put that VLAN in the header and a user role, which we'll talk about maybe a little bit later, but it's putting that VLAN in here. So, and the VTEP knows, hey, I know he needs to maybe a flood alert, so it's going to all the VTEPs, or maybe it already has learned where that MAC address is because of EVPN, so it already knows which VTEP to send it to. So it's going to wrap that up, and it's going to send the traffic to the VTEP's loopback interface via IP. So it's going to cut across the layer 3 network and terminate on the VTEP that this traffic needs to egress on. The packet is de-encapsulated. It's going to get to the point where it's reading the VXLAN headers. The VTEP reads that and says, "Oh, okay, you're for VLAN 100. I'm going to go ahead and de-encapsulate you, and then put you on the VLAN 100 so that the client can hear that traffic." We have this thing called the the group policy ID, which we can insert user roles into. Those familiar with the Aruba world, we've been using user roles for a very long time. So a user role can be derived in many different ways, but it's basically we're assigning a name to a user or device as it comes onto the network. So me as Phil authenticating on the network, I might be authenticated by a radius server, and the radius server is tied into multiple different repositories or IDPs to be able to look at all sorts of variables for my authentication. One might be the security group I'm in an Active Directory, and maybe that security group is an employee. Maybe it's also looking at Intune to know that I'm on a corporate device being managed by Intune, and it's putting those things together to give me a role of employee, because I'm not only an employee, but I'm an employee on a production device. So it gives me the role employee. That sends it down to the switch. I'm in that role, or the access point. The access points also use roles. Now, the device that has that role can implement policy, but now I can also carry the role with me wherever my traffic is going. So as I need to talk to, say, maybe an IoT camera or an IoT device, my role is sent in my VXLAN traffic. So when this gets to its destination, the receiving switch can de-encapsulate that, not only know what network it's going to put my traffic on, but also look at the role. And then it can look at policy to see if I'm allowed to talk to that IoT device. So that's how we're going to accomplish that layer 2 segmentation. Even from same switch to same switch, we are going to realize the role in the VXLAN header so that we can do that microsegmentation. So my role will carry with me wherever my VXLAN traffic is going. And we're going to demonstrate that in a later video. Okay, another depiction here of the underlay versus overlay network. So here, the underlay is the routed infrastructure. So we could say that, again, if we take a look at from a VPN type of encapsulation. So I'm at my house, I'm trying to talk to world headquarters, I'm going to transport across any number of routers across the internet before I get to my destination. So we call that an underlay network. So it's the routed network. How do we get IP packets from a source to a destination across any number of switches? That's the underlay. So in a VXLAN enabled world, that underlay could be anything. Typically it's OSPF for a campus network, but it could be IBGP, it could be ISIS, it could be static routes. But we need to be able to allow this VTEP to know how to reach this VTEP. That's what we're trying to accomplish here. So that's our underlay. Our overlay is just the same thing, but now we have a client that's forwarding traffic that is then going to be encapsulated, like we talked about, to cut across the infrastructure to be de-encapsulated at the remote switch. And again, any number of devices here that we're tunneling across, just like a VPN. Okay. So this screen here is talking about net conductor solutions, and the focus of my videos here are really on this left piece. It's really the left and maybe this DC fabric here because it's doing the similar functions. But net conductor is a orchestration solution to be able to deploy all those personas with a wizard. So as you can imagine, all the stuff I talked about, we're talking about VLANs and any casts or any connect gateways. We're talking BGP. We're talking about EVPN. We're talking about distributing all that with route reflectors. I mean, it can be a very complex configuration to do by hand. So Aruba gives us a couple different methods to do that. One is what we call Aruba Fabric Composer, which is a virtual machine that sits on campus that does that orchestration of the configurations for you with some basic information. And then the cloud component of that is called Net Conductor, which is going to configure your environment based on you bringing this in and you assigning the personas and the networks that are going to participate in VXLAN. It's going to do that configuration for you. Same thing with the DC fabric. So I'm not going to focus on these guys here, but these are Net Conductor also orchestrates it for for access points and SD-WAN and microbranch. It does it for all that, but we're not going to focus on any of that in these videos, at least not these videos. So with that said, that is our basic primer on VXLAN, the components involved, the basics of how it does what it does. And in the next set of videos, I'm going to show you how we can deploy the underlay and the overlay using NetConductor, as well as get into that group-based policy where we use that user role within VXLAN to microsegment traffic. So look for those coming up. Okay, until next time.